Okay, that's good. Okay, we talked about Gödel's proof in, the early 1930s that blew away a lot of mathematicians, including Russell and Whitehouse, whose volumes on this were totally discredited. And he showed that no matter what assumptions you start with, that you end up with something that has that you end up with showing something that's true that you can't prove. That's kind of interesting because if you apply it, for example, to things such as philosophy, ideology, faith, that means that if you have faith, there's things that are true that you can't prove. And this is the reason that people are looking at Gödel even today and looking at the implications of his theorem, and they're just incredibly widespread. It shows that you can't have universal knowledge from finite assumptions and finite experiences. So we gave a proof of that. We said that Stephen Hawking abandoned the idea of looking for a theory of everything because no matter what they prove, there would still be things true that hadn't been proved yet. And so he kind of gave up with the theory of everything. Then we took to the Turing halting problem. Now, the Turing halting problem is something that we proved last time by a reductio ad absurdum sort of argument to show that the assumption of a halting oracle led to an optical illusion, led to a contradiction. Therefore, the halting oracle cannot exist, and therefore it is non-computable. And this is going to have applications to artificial intelligence from the perspective that I'm looking at it at. And we went through these slides where we had the non-computable. We had an oracle up here on the left. We assumed that this halting oracle existed. Then we said that, well, if that halting oracle exists, then therefore we could make it a part of a larger program because it's nothing more than some code. So we're going to lift this up as some code, as a function or a subroutine or whatever you want to call it. And we are going to use it in this larger model. And we show that this led to a contradiction that if a certain program with a certain input halts, then this program loops. But if it loops, it turns out it halts, and it's just a contradiction, and it doesn't work. So that's interesting. And then we talked about the application of this to problems which could be disproved by a single counterexample. And we talked in detail about that last time, so I'm not going to repeat that. But there was Goldbach's conjecture, there was Legendre conjecture. By the way, did you know Legendre, I believe, was on the PhD committee of Joseph Fourier, the guy that did the Fourier transform, him and Laplace. Man, you talk about a terrible PhD committee, a hard one with just famous people like Laplace and Legendre. And they didn't like Fourier's theorem, but they passed him anyway and gave him his doctorate, whatever it was. Anyway, that's Legendre's connection, great mathematician. And then the really big pearl is the Riemann hypothesis, that the real part of any non-trivial zeros of the Riemann zeta function is a half. It turns out it isn't apparent from the formula, but this has a lot of implications for proving theorems about primes. And there's a few theorems about primes out there. I can't rattle them off, but there's a few theories about primes that can be proven if the Riemann hypothesis is true. And it's been tested, as we said, with 10 trillion non-trivial zeros. Wow. And if you could get $1 million if you prove the Riemann hypothesis, and you could prove it if you had a halting oracle. So you can see there's big bucks in actually writing the halting oracle, but as we've shown, you can't write a computer program that does the halting oracle. And then we showed that if you had a Turing halting problem, again, you could solve Goldbach's conjecture. You just simply write a program and you put it to the halting oracle. And if it halts somewhere, the conjecture is wrong because it's found our counterexample. If it doesn't halt, that means it's run forever and it is true. Same thing for the Legendre conjecture and the Riemann hypothesis. A single counterexample just kind of derails it, as we mentioned last time. And then there's a whole bunch of open problems. If you go to Wikipedia and look at open problems in mathematics, there's a whole bunch of them. A lot of them can be proved by a simple counterexample. There's some that can't be. One that can't be, believe it or not, is the what? The twin prime conjecture. Twin primes are primes that are next to each other. They're two apart, like 5 and 7, 11 and 13. Let's see, 29 and 31. So they're right next to each other, only two apart. And the question is, are there an infinite number of primes? That's an open problem in mathematics, which still hasn't been solved. Here's something interesting. I'll mention it in case you're interested in weird stuff like this, weird computer science theory. Suppose that you had a halting oracle. So all of a sudden you had a halting oracle and you put it in with all the computer programs. So we have all the computer programs in the world plus this magic thing called a halting oracle. Well, if you did that, you'd have a new computer system, right? Now, it doesn't exist because the halting oracle doesn't exist. But if you had all computers and you added the halting oracle, this gives you a brand new computing system. And guess what? There's problems there that halt or don't halt. So you have kind of a if you will, halting problem that you can talk about. So that's the halting problem, assuming that the halting problem exists. So it's a second level up. It does turn out that if you have this second level halting oracle, that you can solve the twin primes conjecture. So this is fun that theoretical mathematicians go through it. I find it just fascinating. If you want to find out more about this, yeah, let me take the course in information theory. We talk about this a little bit, but we're engineers. We're interested in things that work, not interested in speculation or wide-eyed sort of things. But I think it's important as computer engineers and practitioners of artificial intelligence, we know that there are things which are non-algorithmic that computers can't do. That's the reason that we're going through this. There are things which are non-algorithmic. Um, and then there's Gregory Chaitin, who is just a remarkable guy. He said some of these things might not be able to be proved. Maybe Goldbach's conjecture will never be proved. Maybe there doesn't exist a proof of it. Maybe it's true simply because it's true, and that it might not be provable. And of course, we can't tell if it's true because it's true. But if we do prove it, we found out that it can be built from lower level assumptions. And these are other open problems which have yet to be solved. Enrica's conjecture, Bocart's conjecture, and the Collat's conjecture, and all of them are just open problems which have not yet been proved. It turns out people check them to a large degree, but in order to disprove it, you have to find a counterexample. If it runs forever and it never halts, well, if you write an iterative program, if it runs forever and it doesn't halt, that means that you've proved the theorem. So there's lots of these, very interesting. And then we mentioned Chaitin's mystical magical number. And this is a number that if you knew that you can solve all of the open problems that require a single counterexample. And this should blow your mind, and you should say that can't be true, because that should be your initial reaction, that this indeed can't be true. But indeed, it is true. And we show this in information theory. And then we show about the unknowable. And I think this has philosophical sort of implications. There are things we know exist that are unknowable. In fact, the next thing I'm talking about is something which is unknowable, and this is a theorem due to Gregory Chaitin, and we're kind of slow down here. We said we could both write a program that computed pi to say 10 significant figures. You wrote a program, I wrote a program. One of our programs is shorter than the other. This implies that there is a shortest program to do that for a given computing system. So if you give me a computing system with a bunch of functions, available subroutines and whatever, then there is a shortest program that you would write, and there exists a shortest program. And we'll never know if we get it, because these shortest programs, which are the foundation of algorithmic information theory, turn out to be unknowable. And this is something that Gregory Chaitin was actually able to show. Gregory Chaitin called the shortest elegant program, the shortest program that could do something, the elegant program. And this is the foundation of Kolmogorov complexity. It turns out that there is the Shannon sort of information theory, and then there's the algorithmic information theory, sometimes called the Kolmogorov information theory. And there were three people that actually developed this. One was Kolmogorov, the other one is Solomonov. Solomonov came to the 1956 Dartmouth conference that coined the term artificial intelligence, and he developed it. And then independently, Gregory Chaitin, as basically a high school student, began to develop algorithmic information theory together. So when I teach this, I don't call it Kolmogorov complexity or Kolmogorov information theory. I call it the Kolmogorov-Solomonov-Chaitin information theory. Now, why was it named Kolmogorov? There's a verse in Matthew, and the verse in Matthew says, "To those who have shall be given, and from those who don't have, even that will be taken away." So it turns out that indeed credit usually goes to the highest profile person in the group. Like if you publish a paper and you publish a paper with your advisor and your advisor is well known, everybody doesn't say, "Oh, this is the graduate student's work." No, they credit it to the advisor because your advisor has a greater reputation. It turned out at the time at the development of this theory, Kolmogorov, who was a Russian mathematician, already had a great reputation. He did the axiomatic foundations of probability theory and a bunch of other stuff. And because of that, his name kind of stuck because of the Matthew principle. It's kind of like he was the professor and Solomonov and Chaitin were the students. And so therefore, everybody called it Kolmogorov complexity. I do that with, we talked about Bringsjord's Lovelace test. Actually, Bringsjord published with a couple of graduate students, but nobody mentions the graduate students. It's always Bringsjord's Lovelace test. Remember, that was the test for creativity in artificial intelligence. So again, there exists no computer program to detect the shortest program. The shortest program to do something is called the elegant program, and it's for a given task T, and it's for a given computing system with resources, and doing so is non-algorithmic. You just can't tell. And here's something which is interesting we're going to talk about later. There are an infinite number of elegant programs of increasing length. So therefore, if you have a very, very long problem, you have an elegant program. There exists one that is so big. No matter how big you make that elegant program, there's always a problem you can come up with where the elegant program is bigger. For example, I said compute pi to 10 significant bits or 10 significant figures. Well, do you think that the Kolmogorov complexity for that is less than computing pi to say 100 significant digits? Yeah, it probably is. So 100 significant digits it has a greater elegant program. And you can make elegant programs there exist, and I think this is intuitively obvious, there exist elegant programs of larger and larger and larger unbounded length. I never like to use infinite because infinity doesn't exist. And a lot of times we say something is infinite, we mean it's unbounded. Unbounded still means finite, but really, really big. So we can make these unbounded and we can make elegant programs of ever increasing length. And I'm sure that it doesn't take much thought to actually to do this. So let's dig into Chaitin's proof, which I think is incredibly intuitive. Just like the halting oracle, we're going to assume that there is an elegance tester, and you give it a program that gives an output, and this program, this elegance tester, says yes, this is an elegant program, or no, it isn't an elegant program. Now, it could turn out that the P you give in is not something which is computable. There's probably a bunch of strings of ones and zeros that don't correspond to any program. And so I put bogus up there also. So the elegance programs could say this is just a bunch of gibberish. You know, it got scrambled in the transmission and a bunch of zeros and ones got screwed up and it just doesn't make any sense. And the program crashed. So this is the elegance tester. So we're going to assume that it exists. And just like with the halting oracle, we're going to show that the assumption of its existence leads to a logical illusion. In other words, it leads to a contradiction. So here we go. Here's what we're going to do. Here was Chaitin's sort of way of doing things. We had the elegance tester, you can see there, and that's assumed to be a computer program. And we're going to also put a counter there. And that counter is going to go, I don't know, 1,000. It's going to count up. You know that all computer programs are a string of ones and zeros. So we're going to have this P, this counter, count up and generate one after the other sequentially all of the programs that exist. Okay? And usually we will do something interesting. And we're going to call this program in the yellow box here ET plus. So we are going to have a computer program that contains the elegance tester with a counter, and that counter is going to be a finite number of bits also. So it's going to add a little bit to ever how long the elegance detector is. And so we have this, and here's what we're going to do. We're going to first of all adopt the notation P is P bits long. Put a absolute value thing around it. So it's a certain length, and if it does exist, then it does have a finite length of its computer program. We're also going to assume that the augmented program, ET plus, is, as you see, ET plus with an absolute value sign around it, bits long. And we're going to start the counter at ET plus bits. So say that the elegance programmer was of, I don't know, two gigabytes long. We're going to start the counter at 2 gigabytes, which is a bunch of ones in a row, and we're going to start with a bunch of ones, and then we're going to start to look at all of the programs that are longer than the elegance tester. And eventually, if this elegance tester is good, we're going to indeed find one. So this is the interesting part, and this gets a little subtle here, so bear with me. So if that ET exists, if that ET program exists, the elegance tester program existed, and it found an elegant program, and this elegant program had a length which was greater than the length of P. Get the idea? So if the ET plus program, say it was 500 gigabytes long, eventually we're going to find an elegant programmer saying 557 gigabytes long. And so it's going to find something which is actually longer than the elegant program. Well, here's the interesting thing. That program found a very large, elegant program that was larger in length than the ET plus program. This is a this is a counter indicator because that P program has to be, well, the elegance programmer detects elegant programs, whether it's elegant or not. Well, P can't be elegant. Why can't P be elegant? It can't be elegant because ET plus computed P. It can't be elegant because ET plus computed P, or the same result as P, with fewer bytes. So it's a contradiction. And the contradiction comes from the fact that the elegance tester must have a finite number of bytes associated with it. So again, we have a reductio absurdum smackdown, if you will, a logical illusion. We have a contradiction. It detected an elegant program, which was longer than ET plus, but ET plus was able to generate and cause that elegant program to be said as or called elegant, but it isn't because ET plus generated that same thing. So it's just a fascinating sort of result. So this is another example of something which is non-algorithmic. A elegance program tester is not algorithmic. We have shown indeed and proven mathematically, if you will, by showing a counterexample to our assumptions that an elegant program cannot exist. Now, one thing that is asked a lot is, well, all of these non-algorithmic things, what about the computers of the future? You know, I think I've shown here, this is a 1947 electronic numerical integrator and computer. And you can see it probably ran on tubes, and it had a bunch of interconnects. They programmed it by actually performing the interconnections, if you will. And this is interesting because I think if we backtrack and we look at what what the future is going to bring. Niels Bohr, who was Danish, quoted a famous Danish saying which says forecasting is dangerous, especially if it's about the future. Now, 1947 was just immediately after World War II. And in World War II, for all of the radios and now all of the computers, we used vacuum tubes. So if you forecast what the future was going to be, you would say, well, you know what we need is more reliable vacuum tubes because these vacuum tubes had relatively poor reliability. And we need better vacuums in the vacuum tube. We need more robust filaments in order to run the vacuum tubes. And that would be the forecast back then. People not looking around the corner and seeing the advent of semiconductors and the use of semiconductors. And I think it's the same thing today. And the reason that we have to be very, very careful of all unsubstantiated claims which have, if you will, delayed scrutiny that is going to happen in the future. We can look at our toes or we can look into the future, but looking into the future is sometimes dangerous. So when you hear that AI is going to do this and that, and there's delayed scrutiny there, you have to you have to take that with a grain of salt because you're not sure if it does or not. Okay, so what about computers of the future? Well, it turns out that Alonzo Church was Alan Turing's PhD advisor. Alan Turing, who was British, came to the United States and worked under Alonzo Church to get his degree. Now, Turing came up with the Turing computer, the Turing machine, if you will, which was the first computer. And Church had come up with something called lambda calculus, which did things like a computer. And so they butted their brains together and they found out, you know what? Both of these things can do exactly the same thing. So the Church Turing thesis is that any computer which follows algorithms uh, can if it followed algorithms today, that same algorithm could be computed by Turing's original machine. Any viable machine that passes the Turing threshold, if you will, any viable machine can do anything. So if you do something on your computer today and you say, wow, that's really exciting, that is not due to your computer. That's due to the underlying algorithmic, the number crunching. Now, it does turn out because of technology, our computers today are thousands, millions of times better than they were at the time of Turing. And computers of the future will be thousands of times better than they are today. But the Church Turing thesis says, look, if you've proven like the elegant theorem detector or the halting problem is not algorithmically possible, then you are not going to be able to do that in the future because the future machines are the ones that are going to be restricted to algorithmic things. So that's the Church Turing thesis. So the principles that I'm giving are the principles that are given are independent of the computing machine as long as it does stuff that can be done by the Turing machine or machines today or machines of the future. The big thing is the power of the machines and how long it takes them to do it. The computers are getting faster and faster. If you look at Bernie Woodrow's 1960 machine, for example, he trained it using gradient descent, but his computers were so slow that it took a long time for him to do it. And today we could just whip by it. I mean, it's just incredible. Another objection is about quantum computers. What about quantum computers of the future? I don't know if any of you have taken the course here in quantum computing. Has anybody taken that course? No. Okay, so okay, Michelle. Okay, you have, and so I think probably the first thing you learn is things like Shor's algorithm and Grover's algorithm. Is that right? Notice the second word in both of those, algorithm. And so both of them assume an algorithm, a step-by-step procedure. And there's other limitations about quantum computers. I think I mentioned that it's kind of assumed that they're going to take the replace of our laptop and make them into super duper computers, but that's not the way quantum computers are built. And I hate to be disparaging, but I first heard about quantum computers 30 years ago, and I think I mentioned this also. And nothing really substantial has happened except some press releases from different companies trying to promote themselves. I don't see any great things happening with this. So I'm skeptical about the future, but you never say never. So maybe we are going to have quantum computers. They keep they keep looking at quantum collapse and keeping coherence is a problem. And did I mention the mystery men in here? Have given a couple talks. Did I mention the mystery men and how I explain quantum mechanics? if you don't remember, okay, so I was approached by the pastor of my church, and he says, "Bob, you're a really smart guy." Yeah, I am. So he said, "I don't understand quantum mechanics." So there was a book written about quantum mechanics and spirituality or something. And here was my explanation, and feel free to use it because I think it's really cool. There was a movie called The Mystery Men, and it was the story about a bunch of superheroes that had substandard superheroes. William F. Macy played the shoveler, and what he did is he had a big shovel that he went around. He was really good at bonking people on the head with the shovel and beating people up with the shovel. He had magical powers. And there were some other ones with some substandard. There was this one lady with a bowling ball, and the bowling ball was a something to do with her dad, and her dad's head was inside the bowling ball, and it did great things. But the one that was really interesting was a guy called Invisible Boy. And Invisible Boy, he had a superpower where he could turn invisible. And he says, "Yeah," he says, "I can turn invisible." And the guy interviewing him, I think it was William F. Macy, and I don't know, the guy that played Pee Wee Herman, what was his name? He was also one of the mystery men. And they said, "Well, we can see you right now." He says, "Yeah, that's the kryptonite of my superpower for being Invisible Boy. I'm not invisible when anybody is looking at me." So I thought that was a great explanation of quantum mechanics. You don't know what a quantum state does. It has all of this ambiguity associated with it, all of these possible outcomes, and you don't know what it does until you look at it, just like Invisible Boy. And if you look at it, boom, it collapses to a single result. So those of you that have touched quantum mechanics know that this is indeed the case, and that's the reason quantum computers are so really great, is because they have all of these different levels that they can work on as long as you don't look at them. And one of the big problems with quantum computing is everybody wants to peak, and they have this quantum collapse, this so-called loss of coherence, and the quantum states collapse before the quantum computing can do its magic. So we'll see. Maybe in the future that will be happening, but this was done, gosh, for at least 30 years. Originally proposed by Richard Feynman, the great physicist from Caltech, who came up with the idea of quantum computing. And boy, that guy was a smart guy. Even though, interestingly, he had a normal IQ. He was just a hard worker. According to him, his IQ did not test that hard, but man, he had a lot of insights, including the idea of a quantum computer. So here's the question: if there are things which computers can't do, does that mean there are things which humans can't do? Are there things which about us which are non-algorithmic? If there are things about us which are non-algorithmic, that means computers will never do them. There are qualities about you and me that are non-algorithmic that AI will never duplicate. They might simulate it, but they'll never duplicate it. So we're going to talk about some of these attributes and talk about why I think that they might be non-computable. Here are the things I'm going to make a case for non-computable. I think the qualia is something which is non-computable. What is qualia? Qualia is a type of sentience. And when you feel pain, you have an experience, right? I'm going to use the example of biting into a lemon. You bite into a lemon and you have this sensation. And that is not algorithmic. Understanding, we will make a case for with Searle's Chinese room, is not computable. It's non-algorithmic. I think that emotion is clearly not that is algorithm. That emotion itself is non-algorithmic. I don't think the computers will ever love, feel compassion, or empathy. We'll make a case of creativity, and we'll define what creativity is, and then we'll talk about consciousness. And there are some implications for uploading yourself, because if there are things about you which are non-algorithmic, then you can't upload yourself into a computer, as some transhumanists are trying to claim. Because if you load yourself up into a computer, you cannot capture the non-algorithmic aspects of your character. And I maintain that without those non-algorithmic aspects, you are going to be a very, very boring person. So let's get into this. Let's get into some of these specifics here. The first one, I'm just going to appeal to your reasoning, and that is the idea of qualia. Qualia is the individual instances of a subjective conscious experience. So if you feel pain, if you feel a paper cut, that sensation that you feel is qualia. If you bite into a lemon and you taste something, that is qualia. If you have an aroma that you smell, that is qualia. That experience is qualia. So we have a lady here biting into a lemon. And of course, everybody's here bitten into a lemon, right? Okay. And so you feel that sourness just hitting your tongue and exploding all over your mouth. And that's a sensation. Now, here's a question. Suppose you knew a guy that since he was born, he had no sense of taste, he had no sense of smell, no sense of taste, no sense of smell. And what you wanted to do is you wanted to duplicate in him the idea of tasting a lemon. How could you explain this to him? Well, you could explain, well, there's this chemistry, there's this acid and base, and lemons are acidic and acids are a little bit more acidic, and so they're going to taste sour. I don't know. Has anybody ever tasted another acid? No, I used to play. My dad used to own a garage, an Arco station, and we changed batteries. And one of the things that the batteries had is sulfuric acid in it. And it's hard to change a battery and not dip your fingers in the sulfuric acid a little bit, and you try to wash it off. But if you taste the sulfuric acid, it tastes sour, just like a lemon. So I don't know, but I think that most of the acids are kind of sour like lemon. So you could explain him that, and he would go, okay, okay. Now, have you duplicated this idea of this qualia in him? No, he still doesn't know how to experience it. You could explain him the biology of the taste buds. You could explain to him the mechanics of biting into the lemon. You could explain them I think they're called pustules. I no pustules. That sounds like a disease. Anyway, those little pods that when you bite in them, they pop out all the juice. I forget what they call them. Um, and you could explain them all of that. But no matter how much you explain to him, you're not going to be able to duplicate that idea of qualia in him. So the question is, and I think you all agree with that, right? You couldn't duplicate it. You could explain it, but you could explain all the properties of it. But the actual duplication, no, I don't think is possible. And if you can't explain this to another person, how are you going to write a computer program to duplicate this idea of sentience? Now, I won't allow you to go to this faith in emergence, where you have an emergent behavior. Things get so complex that they start to develop a personality in emergence. All of that, as we will discuss, is simply a matter of faith, which George Gilder calls rapture of the nerds. That isn't going to happen. So, could you write a program if you can't explain it to this person void of the sense of smell and taste? Can you write a program to do it? No, actually, you can't. You can write a program to explain all of the features that I've talked about, but you're not going to be able to duplicate that. You'll be able to, if you will, simulate it in a computer. I want you to notice something. I have this microphone. Watch this microphone. I put it up here, and it's really nice. Okay, let's see if it stays there. Okay, beforehand, I put it up a little bit and it started to go down. I had to put it up again and it went down. So I'm going to watch this mic. You're under observation there, buddy. So therefore, I maintain that this idea of qualia, that we do not have any sentience, that AI will never have any sentience, because if you can't explain it to a person void of senses, then you're not going to be able to write a computer program and an algorithm that does that. So that I maintain the sentience, which is a subset of, if you will, um, experience, that indeed that isn't possible. So let's tackle another area with more substance. I think a lot of what I just explained to you was a little bit of hand waving and just appealing to your common sense. But let's talk about something else. Let's talk about Searle's Chinese room. I love this example because John Searle was a philosopher and he put this down in 1980. So this was like 45 years ago that he put this down. And I think that the argument is so profound that you notice my microphone? Right? It's moving so slow. It thinks it's getting away with it. It's not. My microphone and I have a good relationship. We have a little fun back and forth, but actually we love each other. Um, So this was put forward in 1980 by John Searle, the philosopher, and has really stand the test of time. Summer Bringsgeorge said, "Yeah, this is really the smackdown in terms of understanding." So here's the idea. It's called Searle's Chinese Room. You can look it up on Wikipedia and a number of different books on AI. Um, but here is the idea. Why did he have a Chinese room? It wasn't because he was a xenophobe against Chinese or anything, but Searle recognized that he did not understand Chinese. He didn't read Chinese. He didn't write Chinese. He didn't speak Chinese. He had no idea what Chinese was. So he said, I'm locked up in this room. And this room we're going to call the Chinese room. And this Chinese room had a bunch of file cabinets. And these file cabinets were filled by a bunch of programmers. Now, I don't know if everybody today knows what a file cabinet is, because I don't think we use file cabinets very much anymore. But I think you know enough to know what a file cabinet is. So, anyway, here's the idea. Searle is in this room and he slipped through a slot in the door a little question, which is in Chinese, like we have on the left here. Anybody read Chinese? I forget what this says.
I know.
Okay, what does it say?
And does the computer can understanding the Q value?
The Q value. Okay, okay.
Oh, it's not Q, it's a query. So like the transformer, the Q of the transformer, like that one. Yeah,
Oh, the Q of a transformer. Okay,
I
okay.
think so.
Okay, well, great. Well, thank you. Thank you. I forgot what it was. It used to be part of my talk, but my memory is kind of going away. So, anyway, he gives this question. You notice that the Chinese statement ends in a question mark. By the way, is this the new Chinese or the old Chinese, or can you tell? Ding. Can you tell if it's the old Chinese?
Oh, this Mandarin.
Mandarin. Okay. Yeah, I know. But Mao
Trans-
Zedong, when he took over China, he says, "Oh, Chinese is too complexicated," and therefore he
I
came up
think
with
it's simplified.
it is a simplified one.
I think so.
Okay. And so I went to all this trouble when I went to Hong Kong to give a few talks. I went and used Google Translate to translate a bunch of slides into Chinese. Of course, I don't know what Chinese is, but you know the way you can use Google Translate and be pretty happy with the results if you translate it to Chinese. Then you give it to Google Translate in Chinese and translate it back to English. And if it does so successfully, you can make pretty sure that indeed that your translation was pretty good. So I did this, and anyway, the people in Hong Kong didn't like my translations. They said it was no good. So I had to use slides without the Chinese translation. And I was just like Searle. I don't read Chinese. I don't understand it. And all of these other things. So anyway, let's get back to Searle's Chinese room. You were given a question, and this question was written in Chinese and slipped through the door. And Searle, who is inside the room, inside the Chinese room, looks at this little sheet of paper. And he looks at this little sheet of paper and says, gosh, I don't understand what this means. I can't read it. But he has all these file cabinets. So he begins to go from file cabinet to file cabinet to file cabinet, looking for a match of this question and something which is filed in the file cabinet. Well, finally, he finds it. It takes a little bit of work, but he finds it. And in the file cabinet, he pulls it out, and there's the question. And right below it is the answer, also written in Chinese. So he meticulously writes down the answer in Chinese. He refiles the card in case he doesn't want to lose it in case the question is asked again. And he's written down the answer in Chinese, doesn't understand anything which is going on. And he goes and he slips it out the slot in the door. Now, the people external to the Chinese room are going to say, wow, whatever is happening in there is really incredible. What's ever inside there understands Chinese, reads Chinese, writes Chinese. No, what is Searle doing? He is following an algorithm, isn't he? He's following a step by step procedure to match what is going on, the question, to things which have been filed in the file cabinet. And the things in the file cabinet have been put there by a computer program. The algorithm has been written by a computer program. And just because Searle can use this pattern matching doesn't mean at all that he understands Chinese, although it appears externally that he does. Isn't that a fascinating argument? Now, it turns out this, of course, was done a number of years ago, 1980, And Searle was using something that they call table lookup. And I think anybody that's done computer science knows about table lookup. Well, today we have much more complicated things. We give a prompt to like ChatGPT or Grok or DeepSeek, and we slip it into the machine. And at the output, there's not a bunch of file cabinets, but rather it runs an algorithm. All of these things that impress us today, ChatGPT and Grok, et cetera, run on an algorithm. So it turns a big crank and it spits out the result. And does Grok or DeepSeek or ChatGPT understand what it's doing? Absolutely not. It is simply following an algorithm. So this is what I did. I gave ChatGPT draw a picture of Searle in his Chinese room. I submitted it through the little slot in the door, and it gave me the answer on the right. It was able to look up on the web a picture of John Searle, and it recognized Chinese, and it was in a room. I don't know if it looked up the Chinese room, but indeed it did. And did Searle, who was running the Chat GPT on the inside, did he understand Chinese? No, he was relying on the algorithm that was trained using Chat GPT. So this, I think, is just a remarkable smackdown, if you will, of the idea that AI understands what it does. It doesn't understand what it does. Very fundamentally, it can add the numbers 8 and 9, but it has no idea, no understanding of what the numbers 8 and 9 mean. Pretty powerful stuff, I think. So that is understanding is non-algorithmic. So that's kind of interesting. Okay, what about creativity? Well, let's talk about creativity. I think we've addressed that AI can't be sentient and it can't understand. Now we're going to talk whether or not it can be creative. Now, one of the things that's done quite a bit, politicians are really good at doing that, is using words, and everybody interprets the words differently. So you can have a politician give a talk and saying, "We must make America great again. We must get people jobs. We must revive the economy. We must have better foreign relations." And of course, everybody on the right and left is going to say, "Yes, I agree with that," because they don't drill down into the definition of what it takes to perform these operations. So we have the same sort of thing with creativity. We must give it a definition in order to discuss it, and you and I must agree on that definition. Now, the test for the test for creativity is named after Ada Lovelace. Ada Lovelace was a remarkable woman. She was the Countess of Lovelace. And in the 19th century, there was a guy named Charles Babbage that built a mechanical engineering that was able to do Turing-like results, Turing-like operations. I don't believe he ever built it, but he shared this with Ada Lovelace, who was just a genius. She is credited as being the first computer programmer in history in the 19th century. And she commented, computers can't create anything. For creation requires minimally originating something, but computers originate nothing. They merely do what we order them to do via programs. This is kind of like Searle's Chinese room, right? It's generating an algorithm. So one of the historical things coming up is the 75th anniversary of the Turing test. Have you guys heard of the Turing test? The Turing test is that can you determine whether artificial intelligence is human or not by a dialogue with it? I think the Turing test indisputably has been solved and met at least at a certain level with the chatbots that we have today. I think it's very difficult to determine the difference. And the Turing test was initially proposed in 1950 by Alan Turing in a paper. And the Turing test is called the imitation game. In fact, Turing's biopic that was in the movie, was starring Benedict Cumberbatch as Alan Turing, is named the imitation game. And they're referring to the Turing test because they're saying, can a computer imitate a human being? And that was what he proposed in his 1950 paper. And that I don't think is very effective because, well, number one, it's been met. And number two, it's only looking at come on. be a nice microphone. Um, it's only looking external to what's happening. Um, like if you go buy a car, you might say, "Oh man, the upholstery really looks nice. Oh, look at that paint job; it's just beautiful. I really like the headlights." And can I turn it on? And you turn it on, and it just hums and it does a great thing. And you say, I love this. I really understand this car. No, you don't. You can't totally understand it unless you pop the hood and look at the inner workings. You have to look under the hood. It's akin to the 1939 movie, The Wizard of Oz. You remember The Wizard of Oz, where he comes out with his big head and said, I am the great and wonderful Wizard of Oz. And then Toto the dog goes over and rips back the curtain, and there's this little guy in there operating a bunch of levers. And it's really not that impressive once you see the guy behind the curtain. So, therefore, to truly understand AI, you just can't look at the results of AI. You have to look under the hood, and that's what we're trying to do. You have to look under the hood, behind the curtain, choose your metaphor in order to understand the limitations of AI. Just like mathematics had its limitations, just like physics had its limitations, AI is going to have its limitations. So you have to look under the curtain, behind the curtain or under the hood to see the way that it makes. Now, I don't know if you remember, but a few years ago there was this guy at Google that said the Google chatbot was sentient. Anybody remember that sequence of stories? He said it was sentient, and Google fired him. His name was Blake Lemoine, and he fired him. Um, they fired him because they didn't defend what he was saying. They said he didn't have the authority to release a news release because he believed this guy was a he believed that AI was sentient and had feelings and maybe even have a soul. I actually interviewed him on a podcast, and he said, "Yeah, who are we to say that the AI doesn't have a soul?" Well, he was not looking under the hood. He was not looking behind the curtain, and he was asked, "How do you know that this is sentient? How do you know this is conscious?" And he says, "Well, I know consciousness when I see it." You notice that he never defines what consciousness is. And I think that consciousness is a very difficult thing to understand. And I think creativity is also, unless we get down to the Lovelace test. So the Lovelace test is as follows. This was proposed by Somer Bringsjord at Rensselaer Polytechnic. And we call it Bringsjord, even though a couple of graduate students were on the paper where he introduced this. And it's named after Ada Lovelace and her claim that AI originates nothing. I think that AI can generate creativity about as much as an iPod. You guys know what iPods are. As much as iPods can create music. No, they don't create music by themselves. You have to supply the input. So here is his test, which is pretty good. A computer program is creative if its output is beyond the intent or explanation of its creator or a software expert. Look at that very carefully. A computer program is creative if its output is beyond the intent or explanation of its creator or software expert. And I think that if that is indeed true, then you're probably having creativity. You notice this idea of creativity is fundamental to the idea of AI writing better AI. Because if AI writes better AI, that means that the original AI that was generated had to be creative and do something beyond the intent and explanation of the original programmer. It has to do something creative above and beyond that. And that's the definite Bringsjord's definition of the Lovelace test. And to date, I know of no case where you have something which has passed the Lovelace test. AI AGI, artificial general intelligence requires AI pass the Lovelace test. Has anybody passed? No, I don't believe so. There's another metaphor which I think you've seen, and that is that for artificial intelligence to be creative, it has to think outside the box. Currently, artificial intelligence, including the chatbots, cobble together things which they have been trained with, and they don't think above and beyond the box. Isaac Newton famously said that he stood on the backs of giants. And what these chatbots do is allow us to get on the backs of these giants quicker than ever before. But the creativity that Newton had above the mountain of intelligence, and he was probably referring to people like Galileo that came before him. What he did was creative. He invented calculus and he invented Newtonian physics. And so this was a creative act above and beyond anything that could be cobbled directly together from from other sources. It was indeed creative, and I think that that's what happens with creativity. Uh, so you have to think outside the box. And creativity requires AI to pass the Lovelace test. Has anyone passed? I maintain that ChatGPT is doing incredible things. And if you've ever used it, you know it's mind blowing. What it does is just incredible. But is it doing anything that it wasn't programmed to do? No, if you look back at the original 2017 paper that coined the idea of a transformer. Transformer is the underlying computer architecture to generate deepfake images and perform chatbots like ChatGPT and Grok. Um, the modern programs are doing what they wanted it to do. This is what they wanted it to do. And the people that wrote ChatGPT is doing what it intended to do. It's not doing anything outside the box, I maintain. So there's a new term out. I just learned it about last week. It's called wide artificial intelligence. Anybody heard that term? Wide artificial intelligence? Well, I'm going to describe narrow artificial intelligence, and then I'm going to explain why it has been, why they're talking about so-called wide artificial intelligence today. This is narrow artificial intelligence. Can AI write music? Well, fundamentally, no. Suppose, for example, you wanted to write a piece of music that sounded Baroque. What would you do? You would take all the Baroque music that you found, you would feed it to a machine, a artificial intelligence machine that would learn from all of this Baroque music. If you're trying to have it generate Baroque, would you train it with anything like modern jazz or rap music? No, you want Baroque music, right? So you stick to the Baroque music. And then what the AI does is it interpolates, it thinks with inside the box. And guess what it generates? It generates something which looks like, or sounds like, I should say, Baroque music, because that's what it's been trained with. Do you think it'll ever generate by itself without further programming? Will it generate jazz? Will it generate things, music written by Wagner? uh, I think it was Mark Twain. If you've ever listened to Wagner, it's kind of always in your face. It's really interesting music. And it was Mark Twain that said, Wagner's music is not as bad as it sounds. I thought that was just a beautiful put down to Wagner's music. Wagner's music isn't as bad as it sounds. Could it generate rap music by itself, just trained on this other stuff? No, it doesn't. So, what's this wide AI? Because now you can go in and you can say, generate AI music and make it, and you can tell it what kind of music to generate. So, therefore, it's much more broader in concept. Well, what the AI chatbots are using now is called a mixture of experts, where you go in and there's this decision of which one of the modules to use or how to use the module. Some of these are so great that they've been able to capture all of these things within one training. But mixture of experts is best understood by the idea of the mathematics. If you go to Google, for example, and you ask it to add a couple of numbers, does it search the web for the answer? No, it clicks into a calculator sort of mode, doesn't it? And therefore, it's a mixture of experts. It looks at the problem. It says, "This is not a web search problem. This is a calculator problem. So let me switch to a different expert. Let me switch to the calculator mode, and I'll be really happy." Stephen Wolfram, who is one of the geniuses in mathematics and is the father of Mathematica. Anybody use Mathematica? Okay. Anybody use Wolfram Alpha at all? No. Okay. Erickson is nodding his head. I don't see everybody, so I only see a few of you. But Mathematica is incredibly powerful because it does symbolic mathematics. And Wolfram, who's well, he thinks a lot of himself, but he should think a lot of himself because he's a really, really smart guy. But he wrote a book, and in it, he says, you know what we should do? This was, I don't know, a few years ago. He said, we should take Mathematica and we should fuse it with chatbot. Do you see my hand raised, by the way? Do you know that this is a computer trying to be smarter than I am? You know why it raised its hand? Is because I raised my hand. It did some image recognition and recognized that I raised my hand. So it thought I wanted to raise my hand. So I don't know. How do I get rid of that? I won't. That's okay. My hand is not raised except in the picture. So Wolfram said, I think that OpenAI should do a mixture of experts and use Mathematica as its mathematics expert. So if somebody asks a math question, don't do a calculator mode, go to a Mathematica mode. And I think this was a genius way of doing it. And if you look at the artificial intelligence today, especially ChatGPT, and you do the paid version, it can solve differential equations, it can do Laplace transforms, it can solve problems in advanced stochastic processes. It's really amazing. It doesn't get all the answers right all the time. You do have to check it like everything else. But this is another example of mixture of experts. If you ask it a new problem, say in physics, that a professor has thought up that nobody has thought up before, it can still address it because it's within the rubric of what it's learned already. But again, this is a mixture of experts, the idea of switching from one to another. So can AI create music? No, it can only interpolate. If you only train it with stuff trained on Baroque music, it's going to generate Baroque music. It's much better now because of this idea that number one, that things are deeper and more wide because of the neural networks are much more complicated than they were. I have a habit of saying complexicated. If I ever say complexicated, no, it's a joke, and that I'm actually smarter than that. It's become more complex, and can handle this so-called wide AI. I think that that's a very nice term. And certainly there's cases where the switch is obvious, such as asking it a mathematical question. It doesn't interpolate with stuff it learned off the web. It kicks into a Mathematica mode. By the way, ChatGPT didn't fuse with Mathematica, but they have written their own equivalent, I believe, of Mathematica because they certainly don't credit Mathematica with the results they give. But it's really, really impressive stuff. So can AI create music? No, it can. It can interpolate among music. Can AI create prose? Well, no, and we're going to talk about why it can't create prose. And one of the reasons is the syntax versus the semantics. Syntax is the statistics of the placement of words. And one of the beauties of the 2017 paper that was the genesis of ChatGPT was the ability to look at syntax and relate the importance of words together. And that just turned out to be an amazingly productive thing. So we do have all of this syntax, all of this statistics among the different words, but it doesn't use what humans use, which is semantics. We use semantics. This is assigning meaning to words. And we're not interested that much. Well, we are a little bit in the syntax, the ordering of the words, but we are more interested in the meaning of the words. And sometimes the ordering changes the meaning, but we're more interested definitely in semantics than meaning. Now, that's very interesting. So this is, can it create prose? Here's another question, and this relates to the idea of AI becoming creative. Can AI write better AI that writes better AI that writes better AI? That's a question that I want to address now with the idea of so-called model collapse. This was a paper written, I don't know, about a year ago, and you can see it has some pretty smart people. University of Oxford, University of Cambridge, so lots of really smart people, and they wrote that yeah, recursion AI writing better AI typically deals with a degradation in quality. It's kind of like, do you ever play, oh, what's the telephone? Where you have a bunch of people in a room and one whispers to the other one and somebody whispers to somebody else and you go around the room. At the end, many times it's a totally different message. It's kind of like that. So here's what these guys did. they trained a large language model, and they didn't have access to ChatGPT. ChatGPT is closed and proprietary, so they wrote their own large language model based on architecture. So they trained it with a bunch of stuff on architectures, and then they began to ask it questions. Then they used that large language model. Let me call it ChatGPT. They use that ChatGPT, the output of that, only to train another GPT, to train another AI. They use the output of that to train another AI. Do you get the idea? So it was the idea of AI training better AI, training better AI, training better AI. And so they did this with this large language model that they had, and they used this generation zero in order to train generation one. They used the output of this to generate number one, generation number one. Then they use generation number one to train generation number two, etc. And they make a claim, and it's covered very nicely in here in terms of the mathematics, that there will be a model collapse. And here's what they got. And this is really fun. This is after the, let's see, I forget which, the ninth generation. So AI, so a large language model writes another large language model that writes another large language model, etc. And here's the result at generation nine. Architecture. Well, at least it got the theme of what it was trained on. Architecture. In addition to being home of some of the world's largest populations of black-tailed jackrabbits, white-tailed jackrabbits, blue-tailed jackrabbits, red-tailed jackrabbits, yellow-tailed jackrabbits, can you see it developed into a blubbering idiot after nine attempts? And this was because of the loss of the information. So I don't think this is a proof that AI can't write better AI. I believe that there has never been creativity generated by AI. But this is kind of I think cute evidence. And the authors made the claim that suppose all of the stuff on the web was written by AI, and then we trained the new AI based on the stuff that was posted on the web due to AI. They said this is really going to dummy down our media and our presentations. That was their conclusion. And they said in order to keep this fresh, you need fresh input from human generated prose in order to update and keep this idea of AI training better AI fresh. You can't just use the AI. You need additional input. Here's a similar sort of problem. This is the Mona Lisa, and I love this. You can do to ChatGPT 4 and you can say, describe this image. So if you give it an image of the Mona Lisa, it will give you a verbal description of it. You know, she has beautiful eyes. She has kind of a smile. She has this interesting background. Her hands are crossed. She's wearing a robe. You can see a little bit of cleavage. She has long hair, and it would generate a very detailed description of this. Now, what you're going to do is you're going to take that description and give it to DALL-E, which is another large language model. Now, DALL-E will take a description and generate an image. You get the idea? So we have an image, we generate a description, then we take that description, give it to another piece of AI, take that description and generate an image. Now we take that image and give it to the first one and say, describe this image. And we repeat this process of describing the image, generating the image, and we repeat it again and again and again. And this is another example of model collapse. Would you like to see what happens when we do that, starting with the Mona Lisa? Here we go. It's actually a fun thing. I'll play it a couple of times. Again, generation of a picture of the Mona Lisa, using that description to generate another image, using that image to generate a description, using that description to generate an image, back and forth and back and forth. Okay, here we go. Everybody see that? Did it come through okay? Let's do it again. What happened is just like in the prose, it kind of becomes a blubbering idiot at the end, right? It generates something with really no foundational information in it, and something that totally is different than the Mona Lisa. And certainly, in any sense, in any definition of the world, it has not generated anything which is more creative. So this is another idea of model collapse and using AI technology to write better AI. Again, I don't think it's proof of that, but I think this is, one of the evidences of it. So that's really interesting. So we have seen that that AI doesn't pass the Lovelace test. What about the Lovelace test for humans? What's the equivalent of a Lovelace test for humans? We say that AI can't be creative because it doesn't generate an output which is beyond the response or explanation of its creators. Okay, well, how do we know that our actions and our thoughts are beyond the intent or explanation of our creator? I don't think it's possible. We don't have access to the intent. Well, we do to a degree, but not totally, of our ability to do things. Here is Roger Penrose's example for this. And let me give you a few examples of this. And we'll do this in the last few minutes. He says that the example of creativity in humans is the flash of genius. You have all had a flash of genius. You've all come up, I have. You've come up with an explanation. You don't know where it came from. You don't know what the heck happened. And the ancient Greeks attributed the flashes of inspiration to Muses, goddess, daughters of Zeus, who blessed certain humans with moments of creative capacity. So creativity was even recognized by the ancient Greeks and giving the credit to a bunch of gods. Um, where did I put that? Okay. Do I have it here? Okay. Oh, it's in the wrong order. No. Okay. No, I'm fine. So there was a mathematician, Jacques Hadamard. Anybody recognize the name Hadamard? There is a Hadamard transform, Hadamard product and matrix manipulation. Yeah, he's a pretty smart guy, but he was interested in creativity also, and he wrote a book on it. And he believed that the flash of creativity in math and science was due to activity in the subconscious, as did Sigmund Freud. If you are a materialist, you have to believe that that comes from our brains, our computer attributes, where there's the assumption that we're made from meat. So therefore, there has to be something there. So he said it was the subconscious, and Freud agreed with him. And Jung, who I believe was a student of Freud, said that he believed the creative inspiration had to come from something outside of the individual. I certainly think that. I think that there is a mind component to this, that the mind is external to the brain or is not totally intersected with the brain, not totally subsumed by the brain. And a lot of this creativity comes from something outside of the brain. He thought it was maybe, this is kind of a new age sort of thing. He thought it was the collective unconscious of all humankind. So, yeah, these people recognize the idea of creativity, the idea that you came up with things immediately. So, let me give you some examples, some anecdotes of people that have had flashes of genius in the history. First of all, there was Archimedes. You're all familiar, I hope, with the story of Archimedes running naked through the streets. Do you remember that? And what he was doing is he was tasked with the idea given to him by the king of the following. The king gave a bunch of gold to this guy and said, "Make me a crown." And the guy made him a solid gold crown. And he got it back, and this king said, "How do I know you didn't mix some lead with this and keep some of that gold for yourself?" And so Archimedes says, "Well, we could weigh it." Well, the person that made the crown was smart enough to make sure that the crown weighed as much as the gold that he was given. And so that didn't pass the muster. So the idea was, well, how can I do this? Archimedes thought about it and thought about it. And one day, while he was getting into a tub of water to take a bath, that's the reason he was naked, he got in and the water spilled out. And he realized the water that spilled out was the same volume of his body that went inside the water. So therefore, if he took that crown and he dunked it in water and looked at the water that was spilled out, that was the water that was displaced by the crown. So not only did you have the weight, but if you will, you had the density. And if it was indeed 100% gold, then that water displaced by the crown should have been the same as the water displaced by by the hunk of gold. And when he got the idea, it was a flash of genius, and he ran running through the street. The myth says, I don't know if it's true or not, but he says, "Eureka, Eureka! I found it! I have found it!" And he was really excited about that. So that was a very early flash of genius. I'll give you another one. Frederick Gauss, who was one of the greatest mathematicians of all time. He was given in grade school the task of adding the numbers 1 to 100 together real quickly. And I love this story. And he was always proud of that. And it was a punishment for the class. The class was bad, so the teacher said, "You must add the numbers from 1 to 100 and give me the answer." And Gauss sat down, and in 30 seconds, he had the answer. And he did it in a very clever way. He recognized that 99 plus 1 was 100, 98 plus 2 was 100, 97 plus 3 was 100, and there were 49 of these. So if you did the first 49 numbers, you got 4,900. Well, you haven't included the 100 yet, so that's 5,000. You haven't included the 50 yet, so that's 5,500. So he did this all in his head, and he was very, very proud of it, and he should have been. I think that that was pretty incredibly cool. And that was one of his earlier flashes of genius. But he said in his work that finally 2 days ago I succeeded in solving a problem he'd been working on, not on account of my hard efforts, but by the grace of the Lord. Like a sudden flash of lightning, the riddle was solved. I am unable to say what was the conducting thread that connected what I previously knew with what made my success possible. So this flash of genius came to Gauss. Very interesting. And he described it as a flash of lightning. What is interesting was there's another guy, and I know you've heard of him, Nikola Tesla, and he invented a bunch of stuff, including the brushless motor. And he said the idea came like a flash of lightning. Notice this is interesting, and I don't think Tesla knew about Gauss's quote. He said came like a flash of lightning. And in an instant, the truth was revealed. I drew with a stick in the sand the diagram showing 6 years later in my address before the American Institute of Electrical Engineers, and my companion understood them perfectly. By the way, anybody know historically the American Institute of Electrical Engineers combined with another society to form what? The IEEE that we know today. So the American Institute of Electrical Engineers was a precursor to the IEEE that we all know and love today. So that was Nikola Tesla's flash of genius. And I think when we get together next time, I'm going to go over some other flashes of genius because I think this really needs to be exemplified enough to drive home the idea that we humans have flash of geniuses. I have had them, and I know that you've had them. You come up with solutions, you don't know where they come from, and you go, "Wow, that was really kind of cool." We'll see it manifest itself not only in mathematics and science, but in the arts where people come up with arty ideas that actually show that. So that's what we'll talk about next time. Okay?